going to talk about bundles in solid fibrations.
Thank you very much. It's a great pleasure, lots of fun being here with a lot of friends. Beautiful city. Yeah, I think I actually like the previous title that I had a little better. It was TBA. It's more reflective of the content of the talk. This talk is the outcome of many years of collaborating with Martin Weinhold, and it's supposed to be his swan song, our last paper together, which will appear soon, maybe, or maybe not. We're not exactly in, we don't see things exactly the same. So to me, the paper is about describing bundles on elliptic fibrations. To him, it's about extensions of M theory and F theory. So we have rather different points of view and emphases. Since it's my talk, I guess I titled it Bundles on Elliptic Fibrations, and I'll emphasize that. I might try to say a little bit about the more genuine physics applications at the end. So I apologize for not really being able to do much with the physics. So this is basically a sequel to a paper on the web from maybe a year ago about ADE transfer. So the basic issue is you have a variety Z, smooth, scalar, whatever. It is fibered over some base B. The fibers are elliptic curves, which means genus 1 curves with a section with a marked point on each of them. And you're trying to study vector bundles V on the total space, or maybe sometimes torsion-free sheaves or things like that. So a good place to start is when B is a point. So Z is one elliptic curve. So in that case, mathematically, the answer is pretty well understood. It's due mostly to Leuenhoff and separately to Bernstein and Schwarzman. And it says that for, let's say for the case, so these are, so V is a G bundle. So G is some reductive group. And yeah, so let's say we start with SLN. Then the answer, the space of all these bundles is just going to be a projective space of dimension n-1. And more generally, for G, it's going to be some weighted projective space of dimension R, where R is the rank of the group. A better way to think about it is inside your group, you fix maximal torus T. So in the case of SLN, that's just the diagonal matrices. And so a T bundle is the same as a homomorphism from lambda to pick or pick 0 of E. So here lambda is going to be the characters, homomorphisms from T to C star. So if you have a T bundle, and you have a homomorphism from T to C star, there's an associated C star bundle. It's just a line. And you get that all T bundles, semi-stable T bundles on E, arise that way. So the moduli space of T bundles on E is just Hom lambda E. The elliptic curve is a group, the set of homomorphisms. So abstractly, this is isomorphic to E to the R. And the point is that any semi-stable G bundle has a reduction to a T bundle. So the map from MT to MG given by the inclusion of T and G. So, and in fact, it's just a quotient. So when the two T bundles give you the same G bundle, if and only if they differ by the action of the Weil group. So in the case of SLN, the Weil group is a symmetric group on n letters. This thing tells you that to give a T bundle is the same as giving n line bundles on the curve of degree 0 and take the direct sum. And down here we're saying that as G bundles, the order of the line bundles doesn't matter, only the set, the unordered set. Okay, so this is the basic observation, and then you just have to compute case by case, and you see that you calculate the W quotient, and you get that it is a projective space or a weighted projective space of dimension R. Okay, so that wasn't too exciting. So let's still stick with type AN, so SLN or GLN. Then there's another way of thinking about it, which is through the Fourier-Mukai transform. So you have E cross E, mapping by P1 and P2 to E. And there's an analog of the Fourier transform that takes bundles or sheaves on E to bundles or sheaves or complexes on the other side. Basically, you take something on one side, let's say V, you take P1 upper star, you tensor it with some kernel of the Fourier transform, and you take P2 lower star of that. So you pull, tensor with something up here, and push down. This P is called the Poincare sheaf. It's a line bundle on the product. Doesn't matter what it is, but it has the nice properties. In particular, it is a concrete way of realizing this correspondence. So given a semi-stable vector bundle on E, you transform it this way, you get a sheaf that's supported just at a finite number of points. That set of points is exactly the n points that we had in the other picture. So let's call that Fourier-Mukai transform of V. This has the advantage that it extends to all bases B. So instead of this picture, you write Z cross over B with Z, which has the two projections to Z. And again, there's a Poincare sheaf on the fiber product, and you define the Fourier-Mukai of V by the same formula. P2 lower star, P1 upper star, V tensor P. And now this converts a bundle on Z into a spectral sheaf on the other side. So a vector bundle on Z, by this interpretation, is equivalent to a spectral cover, B tilde sitting inside Z, so that it's finite over the base. Picks out a finite number of points in each fiber, together with a spectral sheaf, let's say L, supported on this B tilde. And it's just going to be the Fourier-Mukai transform of that sheaf. The transform is essentially symmetric. It can go back and forth in both directions. So in the case that B tilde, the cover, is smooth, L better be a line bundle. If B tilde is allowed to be singular, then L could be a line bundle, or it could be a little more general. It could be any torsion-free sheath. So you start getting different possibilities. And the most interesting cases are when B tilde is everywhere singular, meaning it is reduced. And then you have a bunch of possibilities for what the L is. It still could be a line bundle on B tilde, but it could also be a vector bundle on B. And this is something that is easier for mathematicians to deal with than for physicists. In terms of the rings, if you have an x and a y coordinate, and your equation is something like y squared equals 0, so you have a non-reduced multiplicity 2 spiral cover, a line bundle on B tilde will look like C bracket xy divided by y squared. So it looks like the ring itself, while the vector bundle looks like cxy mod y, 2 copies. So they're completely different as far as interpreting them as modules of the ring are. One is supported on the reduced curve and has length 2. The other one has length 1 but supported on the fat curve. Okay, but this is not the end of the list. You can have hybrids. So you can have something which generically, at a generic point, looks like one of them, but then at a finite number of points, it jumps to the other. So basically, it looks like a line bundle on the fat thing tensored with the ideal sheaf of some finite number of points. So when you tensor with the ideal sheaf, that means that locally it switches to the other picture. So I analyzed some of the possibilities in a paper with Lawrence Ein and Robert Lazarsfeld pretty close to 30 years ago. So we got this picture in the case of K3 surfaces. So for example, if you want to see if you take the tangent bundle of a K3 surface and you look at its Fourier Mukai, so this is going to be something supported on twice the 0 section plus the 24 singular fibers. It's going to look like a line bundle on all of this and all of these, except there are going to be 18 additional points where it jumps like this, where you have the ideal sheaf. These are, if you write the equation of the curve as y squared equals fx plus g, then these points again by something like f prime, g prime, or something like that. You look at the period map, the map from the base to the modular of elliptic curves, and you look at the ramification points of that, the points where the Kodaira-Spencer map vanishes. And those are those 18. So you get a fairly rich structure even in familiar cases. Okay. So this was worked out in the paper by Aspinwall, and then appeared again in one of the papers was Martin. Okay. So what do you do for arbitrary G? There are two things you can do. One is you fiber your space mgz over a relative version. In other words, you send a bundle V to the collection VB, which is V restricted to pi inverse of B. So one elliptic curve at a time. So you're remembering only the vertical part of the bundle. It's restriction to one fiber at a time. So you analyze it and you see that this data is equivalent to some kind of a spectral cover information sitting inside. See, I'm running it's a little hard to get a lot of material in, so I'm going to skip the details. But the kernel of this map, so since this presented the vertical information, this will give you the horizontal data. It's given roughly, very roughly, by homomorphisms L from the lattice lambda to the Picard of B tilde, satisfying various equivariance conditions. So the set of these is going to be some sort of a prim variety of B tilde. So you start with Picard, you take its product with itself R times, and then you impose some equivariance conditions, and you get the prim. So let me just say that this is not quite as good as the Fourier-Mukai transform approach because you get a lot but not all. So let's just be careful and say only some bundles. The buzzword is regularizable. So the local model for these things is you start with G mod T, which maps to G mod N, and this is a W cover. A point of G mod N is just a choice of a maximal torus. A point here is a maximal torus with a Borel containing it. And you get partial compactification, G mod N bar and G mod T bar. And this spectral cover is locally given by this picture. The problem is that for SL2, this is a compactification. For bigger groups, already for SL3, this is not quite compact. It's only a partial compactification. So there could be some things missing. I can give examples if people want. There's a very interesting alternative approach in the case of the exception. So this goes back to work of Loewenchai again, and then it was taken up sometime later by Friedman, Morgan, and Witten. And the key is to look at Del Pezzo surfaces. So a Del Pezzo surface is what you get from the plane when you blow up endpoints. So on DPN, well, the Picard group of a Del Pezzo surface contains an element which is the canonical. Let's call it surface S for short. So the canonical element is a particular element in here. Take everything that's perpendicular to that. That turns out to be isomorphic to the character or root lattice of type En, which tells you that there exists a tautological En bundle. I'm lying a little bit, but I only have half an hour. There exists a tautological En bundle on S, which is this del pezzo end surface. And you can go further and check that on each elliptic curve contained in the surface as an anti-canonical divisor, this thing restricts to a bundle. So you get a map from pairs of an elliptic surface sitting inside a del pezzo to bundles on this elliptic curve. And the claim is that this is actually a bijection. So you get the whole moduli space this way. Going the other way, so this is a description in a paper that I wrote with Gottfried Curio. You start with your V, your bundle. You're trying to figure out an embedding into a del pezzo, so here's what you do. V gives you a map L, same L that I had over there, from lambda to E, which gives me the spectral information. And that gives me the images of the simple roots. The nodes in the Dinkin diagram give me a basis of lambda. Their images give me certain points in E. So now I have E together with a few marked points in it. So take E. So these roots are points in E. E sits inside the plane. You embed it as a plane cubic. In the plane you have a curve, and on the curve you have a bunch of points. Blow up those endpoints. That's the del pezzo. So you get the del pezzo is the blow up of the plane at these root points. So there's an explicit way to describe it. And the point is that this description works in families. So if instead of a single elliptic curve you have a fibration by elliptic curves, it will all fit together. Thank you. Okay. So so let's just say this works in families. Moreover, by work of Conan Leung and various of his students, so there's Chen and Zhang and others, so there's a big industry there where, just to get a slogan, there exists analogs for types Dn and An, and in fact for all others. So in one set of papers they extend it to ADE groups, and then in others they consider auto-automorphisms and extend it further. So there are certain rational surfaces which contain the character or root lattices of these Lie groups in some minimal canonical fashion, in such a way that bundles, G bundles on an elliptic curve correspond to embeddings of a particular type of the elliptic curve into these surfaces. And again, you can do this in families, just like in the case of En. So these are basically obtained from the plane by blowing up a bunch of points, but you're not limited to 8 points. You can go all the way to infinity now. And but then the lattice is not the whole Picard, and it's not even the perpendicular of K. In the case of type Dn, it's the perpendicular of K as well as one other class, which is called the ruling. In the case of A, it's the perpendicular of K and the ruling and a section. So you have to specify some data and look at the lattice that's perpendicular to that. Okay. So finally, let me get to our recent results. So the ADE transform is the following idea. Given chalk. An elliptic fibration, let's call it pi z, and a spectral cover B tilde of B, So I'll specify the cover, but I'm not going to specify the sheaf on it. So this will be independent of the sheaf. Let me tell the mapping to Z. We build some Y of dimension 1 higher, which maps to B. Fibers are DPNs in type EN, or the other long surfaces, ADE type surfaces in the other cases. So this is an object whose dimension is 1 more than Z. And let's let Y hat be the pullback, or Y tilde. So that's going to be Y cross over B with B tilde. So I'm pulling Y back to the family, and we build an integral transform, let's call it T, which is asymmetric. Instead of being based on the Poincaré line bundle, which lives on E cross E, we're going to work with a sheaf that lives on E cross the surface S. So this converts sheaves on Z to sheaves on Y. And very roughly, this kernel, the thing that replaces the Poincaré sheaf, looks like O of D, where D is the universal line. So inside each del pezzo, there's a finite number of lines. You do this over the base, you get a divisor in the base. So very roughly, you take O of that divisor as the basis for your Poincaré bundle. It's actually much more complicated than that. The correct thing is PY hat is going to be OY hat twisted by D, and then you have various corrections. So you have some R sigma cross over B with B hat, and then you end up tensoring with pi B upper star of the canonical bundle inverse. So you make these various adjustments to get the thing to look more symmetric and to specialize correctly. So with these corrections, this Poincaré bundle on E cross S, or on Z cross Y, restricts the previous Poincaré bundle on Z cross Z. So it transforms a sheaf on Z to a sheaf on Y, which when restricted back to Z gives you the Fourier Mukai of the original one. So we're basically extending it in the direction of the lines. Okay. So, back here. Oh, okay. So near generic points, the thing looks exactly right. And what we're working on, part of the reason that the paper isn't out yet, is we're trying to work out canonical pictures near various kinds of singularities of what this transform looks like. But basically, it gives you sheaves that are extensions. So it gives you things like what you got for the K3, things that are supported on non-reduced divisors when you start with singularities like this. So let me just give Martin's picture. So we have our elliptically fibered Z and a bundle V. By the Fourier-Mukai transform, you convert that to Z and some sheaf L, which is supported on a divisor. On the other hand, we have this ADE transform, and there's a version for the other groups, presumably, but we haven't written it down yet. You get this Y of higher dimension and a bundle W on that, which basically induces the V on Z. Z sits in Y as an anti-canonical divisor. And you can do a Fourier-Mukai here to get Y and some spectral sheaf F, where this is again going to be an AD transform. You can also do Y together with a certain cohomology class, or Deligne cohomology class, which is going to give you the G4 flux. And that has less information. So these four are all going to be equivalences. And this is a map that forgets some information. So Martin's interpretation is that this represents heterotic theory. This represents something like type 2b, and this is an equivalence between those. Both things here represent F theory or M theory compactified on this larger Y. So this Y may or may not be elliptically fibered itself, and that's why it includes non-perturbative versions of F theory. Yeah, so like I said, I can sort of communicate it without really any of the details. And but these are augmented in the sense that you have more non-abelian information in them. You have the actual bundle rather than just a class. Taking the class of the bundle gives you the standard F theory that this conference is about. So somehow Martin wants to view this as an enriched form of F theory where you have more information, and you can get the information of F theory from it by basically you take the Atiyah class of this bundle, and that gives you the three form for M theory and so on. So we can check that the diagram is commutative. These are equivalent. This information can be derived directly from each of the nodes. There's a Parseval identity, just like for the Fourier transform. In this, there's a Parseval identity which says that when you convert, you get the same moduli, the same deformation parameters. So deformation spaces for these objects are equivalent to each other. And we check some compatibilities between the Yukawa couplings and somehow the point is that this point of view is supposed to include non-abelian degrees of freedom from the start. So it gives you a hope of being able to treat abelian and non-abelian degrees of freedom somehow on the same footing. So thank you very much.
Is the Y over there Calabi-Yau?
Yes.
It is. Yeah. Then I have a question.
No, sorry, the pair Y comma Z is log Calabi-Yau. So the typical picture is it looks like a DP9 with an elliptic curve in it.
I know you could have more information, but Y as a manifold, is it Calabi-Yau?
It's like a half Calabi-Yau.
So it's non-compact.
Pardon?
So it's non-compact.
Non-compact, yeah. Z is an anti-canonical divisor on it. So the canonical divisor is not trivial. It's all of Z.
Okay, I was going to say that if it was compact, there would be trouble in physics. In this case, that because heterotic string has a higher rank, up to rank 16 or whatnot.
Right. No. So you would say. So I guess you should say that Y is non-compact.
Right. If it was compact, it would be contradiction with heterotic strings.
Right.
You don't want to go rank more than 16, for example.
Yeah.
So in that generality can at best be applied to some non-compact models, and I do not know what the heterotic string would exactly mean with rank more than 16.
Well, the heterotic would be on the threefold.
No, I know, but your what's 10,000 on heterotic side? The rank of gauge group in the heterotic string is bounded, so it's bounded by.
This talk has two parts. One of them lasted 29 minutes, and the other part lasted 1 minute. The 29 minutes were just the math version. Mathematically, it's interesting to build the correspondence between the data on both sides.
I'm talking about the last 1 minute.
For the physical applications, you only want to consider
Yes.
things that fit inside the 8 cross 8 or SO32.
No, I'm just calling that the terminology hydraulic.
Agreed, yeah.
More questions?
So I have a question already regarding the AN case. So as far as I understand it, Bridgeland showed that you have this Fourier-Mukai transform for K3 where you only have at most I1 singularities in the fiber. So is it clear that if you have resolved IN singularities, for example, that the Fourier-Mukai transform exists? And is it clear what the kernel looks like on these geometries?
Well, I'm taking my Z to be a map. You worried about singularities of Z or of the fibration?
Of the fibration. I mean, singularities in the fiber over codimension 1 locus. So, like, if you have a gauge group in F-theory on the geometry, so to say.
I mean, the Poincare sheaf is just defined explicitly. It may not be a line bundle.
So you say it just goes through even if you have...
divisor, not a Cartier divisor, typically. But you can still define the Fourier-Mukai transform for it.
Okay.
Yeah, I don't think there's a problem there.
Yeah, thank you.